let's talk about Eyring activation. So Eyring is a famous scientist, active since the 30s. And he was helping us to understand how, let's say, chemical reaction can be accelerated because certain chemical reactions has an energy barrier, so it would not occur. It sounds a little bit like mechanical chemistry here. But basically, he is recognizing that that if you have certain rate, the way something can happen, or reaction, or your molecular mobility is dictated by an energy barrier. It looks a bit like a Boltzmann concept too. So what happens if that's just a typical case? What happens if you apply stress on it? Well, there is the possibility, so if we call this stress, there is a possibility that the barrier can be lowered. I write it this way because barrier is energy, stress is energy per unit volume, so that little v is some kind of undetermined volume, if you like. So all of a sudden, you have a rate. Now it is a function of the stress you apply. Okay? So as you apply more stress, the rate is higher. And if this is a stress, if you're applying a deformation at a rate of, let's say, epsilon, which is V over L in extension, then you can, it's classical to describe yielding as follows. Then basically you're saying there's no way for yield to occur because my mobility is too low. Well, but it will occur when sigma reaches a high enough value, sigma y, at which the R as a rate is comparable to the applied rate. So you basically imagine, oh, I'm going to deform. The result of deformation is to increase the molecular mobility such that the molecular mobility matches the time scale you imposed or matches the rate you wish to change the shape of the sample. So it's a very, very intriguing concept. So you can claim at that point, yielding occurs. This is what I'm describing so far is classic. It's what people would typically use to describe. So if you look at this, you find epsilon dot over R0 is essentially sigma y t. Right, by equating the two. So if you take a log of this, you'll find that the sigma, take a log of this, and bring this down. You find that aside from a constant, it is log epsilon. So R0 is, of course, some unit of rate that occurs in the limit of infinite temperature. So this expression basically says that your yield stress is logarithmic in the applied rate. It has some truth in it. It turns out this maximum stress, if you call it a yield stress, indeed tend to increase with the applied rate logarithmically. So this is the foundation for us to understand yield, that the stress lowered the activation barrier. Make sense? Oh, God knows why that is the case, but makes sense, right? Yeah. Oh, sorry, I confused you slightly. Eyring originally was working out a chemical reaction case where the reaction can be faster if you apply stress to the system. But that concept has pervaded into the basic discussion of even flow. People think the reason something can flow is because it's capable of hopping over a barrier. In other words, the fact that flow occurs under stress is because stress lowers the barrier. That's commonly said about it. So you can see that has nothing to do with our case of the solid, which initially does not flow. But indeed, we're using this concept of activation to say not necessarily flow, but rather the point of being able to go with the deformation, the yield point, is for me to be activated sufficiently, mobility-wise, so that I can go along with you. So yeah, sorry, I switched gears. It's not chemical reaction anymore, but the concept of the barrier can be lowered by stress is the key concept being used here. So so we should be all happy about this and go home. You noticed if this logic works, all of our polymer glass should yield. If you just follow this logic. Agree? Because give me stress, I lower my barrier so that my mobility eventually reaches the applied rate. So I will deform it. And therefore you realize this is insufficient because polystyrene does not yield. There are polymers that are brittle in the sense it only goes there and it breaks. So what's missing? What's missing here? That's actually you are start to speculating in the right way. It turns out, since you mentioned it, our current discussion is looking at just one temperature. Conveniently, it could be just room temperature. And we know polystyrene is incapable of yield, of going along with your drawing, and it refuses to do so, it breaks. So temperature, yes, so keep going, keep thinking. So it turns out we say polystyrene is brittle. Well, if you warm up your polystyrene properly prepared, okay, extruded, very defect-free, your polystyrene will turn ductile at, this is a wonderful point, at 70 degrees, for example, which is still 30 degrees below TG. It's still glassy. So you're touching a wonderful point. The temperature does play a role. And now the question gets shifted. Why styrene is brittle below 70 degrees? In other words, what we discussed so far will apply to all polymers when they are ductile. For example, styrene above 70 degrees. It obviously does not explain a polymer glass that is brittle. And so what's missing? As Sophie just said, yeah, because you're sitting at the temperature too cold. What does that mean? Huh? Well, we're already below glass temperature. So we're saying, gee, how far below TG I have to be to lose the ability to be ductile, to lose our ability to yield. This has remained unanswered for quite a while, until recently. So what's wrong with this? This powerful idea of stress activation has its limit. And let me give you the answer, unless you can speculate right now for me. May not be trivial. And in fact, what I'm going to explain to you was an amplification of what eventually one discovered, and then come back to say this in a more pedagogical way. Okay, pay attention to, see, this is all about how complete our thinking is. Pay attention to what was stated. Barrier will be lowered if you give me stress. I carefully phrased this word, this sentence. If you give me stress, the barrier will be lowered. Okay? Where does that stress come from? Who is to deliver that stress to you? God cannot do it. to your polystyrene. This is the key question. Where does the stress come from? When can you claim that the stress will be supplied? Infinite amount, meaning as much as you want until the barrier is low enough. So what's missing? If I already told you, you need to explain where the stress comes from, then what's missing? Then what we should answer? Then we should answer, what gave me the stress? Right? What gave me the stress? Can you still have stress building up, which is what you see here? And the black one shows it doesn't build up, it just breaks. And therefore, what does break mean? Well, clearly, it's a termination of the delivery of stress. If I want to preserve the Eyring idea, even no, as conservative as I want to preserve that idea, so it seems we need to work out another layer of the theory, a layer that describes how to supply the stress, which is not the job of Eyring. As I made a remark that the mechanical chemistry is nowadays done that way. In other words, by force, some chemical reaction can occur, meaning ring can open, so on and so forth. And very typically, in fact, this is so amusing, very typically, to achieve that, to achieve the force, which really, the stress ultimately is about force, molecular force on the molecules, for mechanical chemistry. To deliver the force to the molecules, there's a cheap way the mechanical chemistry the people do. You ultrasound it. You put your system in ultrasound, apparently. Well, we don't have ultrasound. We have our polystyrene. We have our polystyrene at 70 degrees. It's capable of seeing stress delivered and yield. We have a bulk sample where the only way stress arises is when I stretch it, where the force, molecular force, will keep rising if I'm able to make sure that I can still stretch. In other words, the styrene does not fall apart. So we need it seems quite obvious. This is all in retrospect, actually. We actually had to struggle quite a bit to get to this point. Now it looks all transparent. But it seems like we have to ensure that there is something that delivers the stress. There is something that causes the mobility to keep rising until it matches the applied rate. And that something is a structure. In other words, keep in mind when you have a sample this big, they are 10 to the what? You know, you do the math. I mean, if it's 10 millimeter, or if it's 10 centimeters, 100 millimeter, your molecular size, not molecular size. This is where I said about rheology. Your mesh size, entanglement mesh size, is on the order of, let's say, 6 nanometers. Let's say, so on the order of 10 nanometers. And that's what? 7 order magnitude? Okay? 7 order of magnitude, 10 million of these things. Allow me to draw them again like this. There will be 10 millions over there. Well, that's all I know. I mean, tell me otherwise. If you have a different insight, let me know. And on this end, and I'm holding this end, and then I try to draw. And the other end, I hold it, I try to draw. 10 million between them. So this network is under deformation. And it's through this network I'm delivering the forces everywhere. Yeah? So although I'm only touching the two ends, I'm delivering the deformation arising from it is the molecular force everywhere along this 10 million. Can I always be successful in doing so? That's the question. It seems to, no, we don't need more to know that that's the question. And apparently, if it's warmer, I could do it. See, that's the temperature thing. That's wonderful. The temperature, remember, for polymers is about the most important external variable besides stress. They're just two variables, stress and temperature, or deformation and temperature. So we hit a home run here, meaning we hit something very deep and very simple. Can this 10 million layers keep accommodating the fact it's getting further drawn? So you can speculate what temperature does. Yeah. Yeah, so you can say the free volume is increasing somewhat. The magic of what temperature does. It is where the nature of glass transition is unknown as well. Because if you look at this temperature change, it's very weak, even though it's in the exponential. How come in a few degrees this rate just plunging towards zero? I'm talking about above TG again, right? Coming down and just all of a sudden you just vanishingly small mobility now. Even though the temperature didn't. So this expression I wrote here definitely cannot explain glass transition. And that's where, at the zeroth order, that's why the glass transition problem is unsolved. It's seeming very innocent, a few degree change. So we'll come back and say more about, expand a little more, ultimately to address the question that's obvious, that Eyring would, if you only have Eyring, it would say all polymers will be ductile. And now we realized the flaw in that argument is you assume the stress is always available, but it's not. And so we must worry what can deliver the stress and cause the mobility to keep increasing. And that obviously turns out is a structural question. Why I say it's a structural question? Because it involves 10 million layers. Same as rheology. Remember we had the shear experiment, 1 millimeter. You cannot dictate how the middle between the two boundaries is being sheared and deformed. Remember, you have the pray to God. Only you can control is the top and bottom. Same is here. And that 10 million layer, now it's 1 millimeter. That's 100 times smaller. So that's why we have 100,000. That's 100,000 layer because it's a 1 millimeter instead of 100 millimeter. That 100,000 layers, again, you only control the top and bottom. The 100 million layers, they do what they want or whatever the Mother Nature or the physics you find out to be. So that's where the issue is. You don't dictate what's inside the 10 million is doing. So we'll come back to talk about that in some depth next time. Any questions? Let's see. Stop here.